Okay, so for this conversation, we're going to talk about making ionic compounds. And the last one we talked about making ions, right? And we made ions, of course, so that we could make ionic compounds. That's where we're going to see them in nature. So our learning goal is to consider charge balance. In other words, how are things going to match up? So if we use charge balance, we're going to write the correct formula for an ionic compound. And we're going to also appreciate, may be obvious already, that ionic compounds consist of both positive and negative charges held together by strong electrical attractions between the oppositely charged ions. Okay, so a couple properties of ionic compounds. I don't think these are obvious. You may want to write these down and memorize them. Ionic compounds, well, this one's obvious. They consist of positive and negative ions, cations and anions, right? They have attractions called ionic bonds between the two charges, okay? But this part I would not say is obvious. They have high melting points and they're solids at room temperature. I mean, I guess you can appreciate that sodium chloride, salt, is a solid at room temperature. So maybe that'll help you remember that. And you might have to simply memorize that they have high melting points. All right, so let's look at this. Sodium chloride is an ionic compound. It's a great example. What we do with sodium chloride is we take sodium metal, which is a soft gray, right? A soft gray malleable substance, solid, right? And it's a bunch of little atoms, a bunch of little atoms that are in an array. And we take chlorine gas, which is green, okay? There's chlorine gas in there, nasty stuff, right? And we take electrons from the sodium atoms, and we give them to the chlorine atoms, and we end up with sodium plus and chloride minus, right? Chlorine minus. So after they become ions, then they go together in a white crystal that we call salt. Now, if we could look at this really closely with, say, a very strong microscope, we might see crystals that look like that. Okay? There is no microscope that is good enough to help us see the actual atoms down that small. But if we could see them, we would find that it was just like stacking of the chloride and the sodium ions. Just one chloride, one sodium, one chloride, one sodium, one chloride, one sodium. And it's three-dimensional, right? It just goes in three dimensions infinitely until it gets to the edge of the crystal, right? So that's how sodium chloride looks like. Now, if we're just looking at one atom, I sort of did this on the previous slide. You have a sodium atom, and it donates an electron to a chloride. Well, it gets a lot smaller because that electron is an electron cloud. So this then, when the sodium no longer has that extra electron, we call it sodium. When this chlorine atom gains an electron, it becomes bigger, and we call that chloride, right? And that positive and negative are what keep that thing together. Now, since they both have a negative, or a one charge, a negative one or a positive one, they're evenly matched, right? So what we need to appreciate is that the total positive charge must equal the total negative charge, no matter what we do. So in this case, -1 and +1 gives you 0, right? But what happens if we take a magnesium atom, right? And a magnesium atom has 2 extra electrons in its outer shell, and it's going to donate those to 2 separate chlorine atoms. Well, when it does, it's going to end up as an Mg2+, right? And there's going to be 2 chloride ions, okay? So the actual compound that we're going to get with magnesium and chloride is going to be MgCl2. And this is the reason why. Because the positives and the negatives have to match up. Here's an example of when you have sodium and sulfur. Sulfur has a capacity for 2 extra electrons. There's only 6 here in sodium's in sulfur's outer shell, but it wants 2, right? So it's going to become sulfide. We learned that in a previous conversation, that sulfur is in group 6. It's going to have a tendency to take on a 2- charge. Sodium's in group 1. It's going to have a tendency to take on a 1+ charge, right? Well, the positives and the negatives have got to match up, and so we do like that. It's going to take 2 sodiums to evenly match up with that -2 sulfide. Okay? Really, the word we're looking for is the lowest common factor, or the lowest common multiple of that, right? We don't need that term, I guess, but that's what we're doing. Okay? So let's finish out this conversation with a learning check. Pause the video and give the ionic formula of the compound formed from barium 2+ and chloride ions. Okay, let me suppose that you paused it. You're going to have barium 2 plus, okay? And if you put one chloride ion in here, it's not matched, right? It's 2 plus and 1 minus. So we still have to put, still got too many pluses. So if we put another chloride ion in here, aha, there we go. 2 minuses and 2 pluses. 2 plus. Right, can you see that? Is going to be equal to 2 minus 2 is equal, it's supposed to be equal to 0. They got to match each other out, right? All right, so we'll be doing more of that in our exercises, and I hope that's helpful.